Hi, today we're going to show you how to use the DMU Kinematics workbench using this simple product shown in front of you. We're going to be using Catia V5 release 18. The product shown consists of a base, a cylinder and a slider, and the cylinder and the slider are connected using a conrod. The way this will work is as the cylinder turns, the conrod pushes the slider up and down the base. To simulate this product in DMU Kinematics, we need to create joints. There are two ways one can create joints. We could have either constrained them in assembly, and then using the assembly constraint conversion tool, we could have created the joints in DMU Kinematics. Or you can directly create the joints in DMU Kinematics. We are going to use the latter and directly create the joints in DMU Kinematics today. To switch over to the DMU Kinematics workbench, click on Start, go to Digital Mockup, and click DMU Kinematics. You will notice that all the toolbars have changed, confirming that we are in the DMU Kinematics workbench. To create a successful simulation in DMU Kinematics, one requires two things. We need a fixed part, which today will be our base, and you also have to make sure that your degrees of freedom are 0. The most important toolbar in the DMU Kinematics workbench are the kinematic joints. For today's simulation, we are only going to require a revolute joint, that is between the cylinder and the base, and also between the cylinder and the conrod. We will also use a prismatic joint between the slider and the base, and a cylindrical joint between the slider and the conrod. Okay, let's get started by fixing the base. We also need to create a new mechanism, so just hit the new mechanism and say OK. We have just created a mechanism called mechanism 1 as shown in the mechanisms branch of the specification tree. To fix the part, select the part and you'll see a green anchor appear next to it, confirming that the part has been fixed. We can now go ahead and create our first revolute joint between the cylinder and the base. To create a revolute joint, we require two lines and two planes. The lines we are going to use today are going to be the center line of the hole of the cylinder and the center line of the protrusion on the base, and the planes are going to be the corresponding planes, that is the plane at the back of the cylinder and the front of the base. To make sure that you've created the joint correctly, click the update button and say OK. If the parts move together as expected, you have successfully created the joint. Now let's create the prismatic joint between the slider and the base. The prismatic joint is much like the revolute joint. You require two lines and two planes. The lines you're going to select are going to be the top front edge of the base, the front bottom edge of the slider, and the two planes are going to be the corresponding planes, that is the plane on the top of the slider and the planes at the bottom of the slider and the top of the base. We also need to create a revolute joint between the cylinder and the conrod. For the two lines, we are going to use the center line of the protrusion and the center line of the hole of the conrod and the corresponding planes. We also need a cylindrical joint between the protrusion of the slider and the hole of the conrod. As you can see, the mechanism sits together as expected. Even though all the joints are created, the degree of freedom is still 1, indicating that this mechanism cannot be simulated. To successfully simulate the mechanism, we need to make the degree of freedom 0 by creating a command. The driving command we will use is going to be for the revolute joint between the cylinder and the base. To do this, double click on the revolute and check the angle driven box. Now click OK, and you can see Catia informs us that the mechanism can be simulated and the degrees of freedom have gone to 0. To create a simulation, click on the simulation button and select mechanism 1. To automate the simulation, click insert and automatic insert and change the loop mode as shown. Now run the simulation once and hit play, and Catia will replay it for you. As you can see, the simulation runs successfully. Now that we have created a basic simulation, let's see how to create a simulation where the speed and timing are governed by us by laws that we have inserted using the knowledge-ware toolbar. To do this, we're going to use the relationship theta, the angle, is equal to the angular velocity times time. The angular velocity we're going to use for today's tutorial is going to be 360 degrees per second. To insert the law, click on the formula icon in the knowledge-ware toolbar. This is indicated by the f of x icon. To show the relevant parameters, click mechanism 1, and you see that the two parameters that we need, that is the angle and time, are displayed. We're going to add a formula to the angle. Again, there are a lot of parameters here. To show only the required ones, click on mechanism 1. We're going to make angle equal to the angular velocity, which is 360 degrees per second times the time. Once you have done this, click OK. Once we have created a law, you will see that the law branch of the specification tree has been populated with our formula. We now need to create acceleration and speeds. That is, we need to select the part that we wish to analyze and whose acceleration and velocity we are going to graph today. To do this, click on the speed and acceleration icon. The reference product is going to be a fixed part, which is the base, and the point that we are interested in, that is the point whose linear acceleration and linear speed we are going to plot versus time today, is going to be the top right vertex of the slider. Once you have clicked OK, you will notice the specification tree has been updated under the speeds and acceleration branch. We are now ready to create a simulation with law. To create the simulation with law and to get the graphs you need, click Activate Sensor. This will show you the list of variables we can plot with respect to time. Clicking on a parameter changes the observed column from no to yes, meaning that Catia will now plot it for you. Clicking it again puts it back to no. Today we are interested in the linear speed and the linear acceleration of the slider. But you should be careful and make sure you're doing it along the right axis. Today our slider is moving around along the y-axis, so we should click linear speed and linear acceleration in the y direction. Once you have done this, run the mechanism once to update the data. As you can see, the simulation is going to run for 10 seconds. We can change this if we want by clicking on this icon and changing the time. Now that we have populated some data into Catia stack, we can graph this with respect to time by just clicking graphs. As you can see, the green lines represent the linear acceleration versus time, and the yellow lines represent the linear speed versus time.